I'm Aviv Yehezkel, a PhD student in Technion, Israel, presenting the paper A Minimal Variance Estimator for the Cardinality of Big Data Set Intersection, co-authored by Reuven Cohen and Diran Katzir. So the set intersection cardinality problem gets two streams of elements and seeks to estimate the cardinality of the intersection. For example, for these two streams, A is A, B, C, D, A, and B, and B is 2A's, 2C's. The intersection includes only A and C, whose cardinality is 2. This problem is very interesting mathematically wise, but not only. It has really many real applications also. For example, optimizing join queries between very big tables. Should we first join tables A and B, or tables B and C, or maybe joining tables A and C first is most efficient? This decision is practically made by the query optimizer, which estimates the cardinality estimation, the set intersection cardinality of each two tables in the join query, and decides to begin with the pair of tables whose set intersection cardinality is the smallest, in order to optimize the query execution. Another application is finding how many users visited your site, both today and also yesterday. To this end, the set intersection cardinality between today's users and yesterday's users is needed. Another one is finding similar documents. For example, detecting plagiarism. This can be made, for example, by estimating the set intersection cardinality of two documents and detecting plagiarism if this cardinality is too large. It's very easy to find exact solution by maintaining all distinct elements already seen in A and B in hash tables, and then comparing these two to find the exact intersection. Though it's easy and exact, it's very expensive and not scalable when the streams get large. In this case, we want a sketch-based solution. The idea is to store only a summary, a small summary of the data, which is called a sketch. So there is no need to store all the observed elements, and then use some statistical algorithm on this sketch to get a good estimate. The questions when we try to come up with a sketch-based algorithm is first, which sketch to store about the elements, and second, which algorithm to use on this sketch in order to have accurate estimation, which are both unbiased and small variance. So the main idea is to hash all the elements in A and B to random variables in the interval between 0 and 1, and then store only the maximal hash value in each stream. Let's denote them XA and XB. From these maximums, the cardinalities of A and B can be easily estimated using these maximums. The intuition is, if there are 10 distinct elements in A, we expect these hash values to be spaced about 1/10 from each other. So the maximal hash value in A should be expected to be about the cardinality of A by the cardinality of A plus 1. And so as well for B. And if we store these maximal hash values, we can just solve this one variable equation to get an estimation for the cardinalities. For example, consider this stream of elements, C, D, 2 B's, Z, D, B, and D. We first hash these elements to their random variables between 0 and 1. Assume that the hash value of Z is 0.05, C is 0.1, B is 0.55, and D is 0.75. We get this mapping from the elements to their hash values between 0 and 1. And as you can see, the maximal sketch in this case is the hash value of D, which is 0.75. Then, using the equation from before, we can solve it to get an estimation for N, for the cardinality of this stream. We get that the estimated cardinality is 3, but actually it's 4, so not very correct. In order to have better estimations and reduce the estimation variance, we don't use only one hash function, but m hash functions, and repeat the procedure from before. We hash all the elements in A and B to hash values between 0 and 1, and store only the maximal hash value of A and B. So in total, we have only m maximal hash values memory for each stream, for A and B, which is small and constant. back to the set intersection problem. So there are three previously proposed sketch-based schemes for this problem. The first one is using the well-known inclusion and exclusion principle. The cardinalities of A and B are estimated, and then the cardinality of the set union is subtracted to get estimation for the set intersection cardinality. The two other schemes are based upon the Jacquard similarity, which is, as you can see there, defined as the ratio between the set intersection and set union cardinalities. And these two schemes first estimate this Jacquard similarity and then use some algebraic manipulations on it in order to get estimations for the set intersection cardinality. The main trick in these three schemes is that both the set union cardinality and the Jacquard similarity can be estimated using maximal sketches of A and B. For example, for the set union cardinality, notice that the maximal hash value of the set union is simply the maximum between the maximal hash value in A and the maximal hash value in B. So using the max sketches of A and B, we can obtain max sketch also for the set union and use similar algorithms to estimate its cardinality. Our main contribution in this work are as follows. First, an analysis for the first time of the statistical performance of these three previously proposed main schemes. Second, a new estimator based on the maximum likelihood method, which outperforms the three previous schemes, is presented and analyzed. And third, our new estimator has asymptotically optimal minimum variance among all min-max sketch-based schemes. And we also give an explicit formulation for this optimal variance. So the main idea is the maximum likelihood method, which is a well-known method for estimating the parameters of statistical model. Generally, we have a set of data samples and assumed underlying statistical model, and the maximum likelihood just finds the values of the model parameters of the assumed model that maximizes this likelihood function. Namely, that maximizes the agreement between our assumption about the model and the given data samples that we have. So our new scheme finds the probability density likelihood function of the set intersection problem. Let's denote it as the likelihood of the probability density of S to be the maximal hash values in A and T to be the maximal hash values in B. Then our new scheme looks for the values of the set intersection cardinality that maximizes this likelihood function. In order to derive the likelihood function, we begin with one hash function and then generalize for all the M hash functions. So the likelihood function is derived according to the three possible relations between the maximal hash values in A and B for this kth hash function. They are whether equal or one is bigger than the other. For the first case, the maximal hash values are equal one to the other. Let's denote N and U to be the set intersection and set union cardinalities. In this case, the likelihood, given that the two maximal hash values are equal and equal to S, it can be obtained by summing over the n possible elements in the intersection. Each of them can be this maximal hash value, multiplying by the probability of each of them to be the maximal hash value, which is the sum from 1 to n of S power U minus 1, because this is the probability of each of the values of the elements in the intersection to be the maximum among the other U minus 1 elements that are in the set union. So in total, we get n by S powered U minus 1 as the likelihood for this first case when the maximal hash values are equal. The second case is when the maximal hash value in A is smaller than the maximum in B. Now we denote A as the cardinality of A and beta as the cardinality of the set difference of B and A. In this case, given that the maximal hash value in A is smaller than its companion in B, two terms must be held for this case. The first is that the maximal hash value in the set difference of B and A must be equal to the maximal hash value in B, which is T. given that the likelihood can be obtained similarly to the previous case by summing over the beta possible elements in the set difference. Each of them can be this maximal hash value, multiplying by the probability of each of them to be this maximal hash value. And similarly to before, we get that this is equal to beta times t powered beta minus 1. The second term that must hold is that the maximal hash value in A need to be equal to S. And the likelihood given that can be also obtained by summing over the A possible elements in A and multiplying by the probability of each of them to be the maximal hash value. And we get this result. Finally, multiplying these two terms obtain us the final likelihood for this for the second case when xa is smaller than xb. So we derived the likelihood function for the first two cases when xa is equal to xb and when xa is smaller than xb. The third case is symmetrical to the previous one, and we get the final likelihood function for the k-fash function. In order to write it in one single expression, we use these three indicator variables, indicating what is the relation between the maximal hash values. I1 gets 1 if we are in the first case, if xa is equal to xb. I2 and I3 are for the second two other cases respectively. Finally, we put these indicator variables in the likelihood functions that we got for each relation and obtain the final likelihood function for the set intersection problem for one hash function. Then we can generalize it for all the m hash functions we have by just multiplying it for the m hash functions and using indicator variables for each hash function. Taking log outside, we got the final log likelihood function. As you can see, this log likelihood function is concave. It's sum of only linear and logarithmic functions, and therefore it must have only a single global optimum to this function, which is great because we can now find this global optimum using maximum likelihood. And that's exactly what the new scheme does. It finds the maximum of the log likelihood function, which is the root of its gradient. And this will be our estimation for the set intersection cardinality. Practically, in order to do this, because the log likelihood function cannot be solved analytically using the maximum likelihood, we're using iterations of the Newton-Raphson method on the log likelihood function using its gradient and Hessian matrix in order to get estimation for its gradient, for the root of its gradient. Notice that in order to use the Newton-Raphson for this problem, we need to inverse a 3x3 matrix, which is quite simple. So there is no real problem. This is the formally statement of our new scheme. It gets the sketches of A and B, the maximal hash values in A and B. First, it estimates an initial estimation for the cardinality of A, B, and the set union using any cardinality estimation algorithm. Second, it estimates the Jacquard similarity, also from these given sketches. And then it runs iterations of the Newton-Raphson method, and in order to find its maximum, and returns it as the estimation for the set intersection cardinality. So, because our new estimator is based upon the maximum likelihood, it guarantees to asymptotically achieve optimal variance with respect to any algorithm based upon the max sketches, which is very good because all main previous works, and especially the three that we discussed before, the three main previous works are all based upon such sketches. So our new estimator is theoretically guaranteed to outperform them. In order to estimate this, to compute this optimal variance, we use the Cramer-Rao bound, which states that the inverse of the Fisher information matrix is a lower bound on the variance of the estimator. we compute the feature information matrix from the log likelihood function and compute its inverse in the relevant term in the matrix to obtain this final optimal variance of any unbiased estimator for the set intersection cardinality problem, which, as said before, is theoretically guaranteed to be the optimal, to be the variance of our new estimator. For the simulations, we estimate the set intersection cardinality for each of the 3 previous schemes and also our new scheme. We fix the cardinality of A to be 1 million different elements and use different intersection sizes from 0 when the intersection is empty to 1 when the intersection is complete A, and different ratios between the sizes of B and A, either 1 when the the 2 sets have equal size, 5 when the cardinality of B is 5 times A, and 10. We repeat this test for 10,000 different sets and average the results to obtain the bias and variance of each scheme. So in this slide, we can see the simulation results of the percentage improvements of our new scheme versus each of the 3 previous schemes. Each column is showing the improvement of our new scheme versus one of the schemes, either scheme 1, 2, or 3. The first row is for 10,000 hash functions used, and the second for 1,000 only. And each figure shows the percentage improvement for different intersection sizes from 0 to 1, and different ratios between the sizes of B and A. So let's focus on 2 figures, for example. Let's begin with this one, the left one. So this figure shows the improvement of our new scheme versus scheme 1, which is based on the inclusion and exclusion principle. We can see that our new scheme always outperforms this scheme, this inclusion-exclusion scheme. And the improvement varies from 100% when the intersection is empty to about few percent when the intersection is the entire A. We can see that overall our improvement decreases as the intersection increases. But it also, in addition, we can see that our improvement increases when the ratio between the size of B and A increases. For example, for intersection rate of 0.6, we can see that our new scheme is about 20% better than scheme 1 when the sizes of the sets is equal, but this percentage is improved to about 60 and 70% when this ratio between the sizes is increased to 5 and 10. Let's now look on this figure, which shows the improvement of our new scheme versus scheme 2, which is based upon Jacquard similarity. We can see here that unlike the improvement versus scheme 1, here the improvement increases as almost always, except for the case of equal sizes, is always increases as the intersection increases from 0 to 1. And again, from about few percent when the intersection is empty to about 80+% when the intersection is entire A. And again, we see that our new scheme improvement increases as the ratio between the sizes increase. As you can see that, for example, for 0.6 again, it's increases for about 30% to 50 and beyond percent when this F increases from 1 to 10. So overall, we can see that our new maximum likelihood estimator outperforms all the 3 previous schemes for all values of intersection sizes and ratio sizes between B and A, and this improvement varies between 100% to about few percent. This slide shows the comparison between the simulation results and analysis results. It means that the first row is showing the percentage improvement of our new scheme according to the analyzed variance of our new scheme versus the analyzed variance of each of the 3 previous schemes. And the second row is the simulations from before. So first we can see that also according to the analysis, our new scheme outperforms the 3 schemes always for all intersection sizes and ratio sizes between B and A. More interestingly, we can see that there is very much agreement between the graphs of the analysis and the simulations, showing that the simulation results match the theoretical analysis very much. So, for summary, a maximum likelihood approach for the cell intersection is thoroughly analyzed, and this new approach is simple and accurate, outperforming the 3 known schemes. Thank you. Questions?